Optical gyroscopes. Optical gyroscopes operate by sensing the difference in propagation time between counter-propagating beams traveling in opposite directions in closed or open optical paths. A rotation-induced change in the path length generates a phase difference between the counter-propagating light beams. This rotation-induced phase difference physically consists in the Sagnac effect, being the basic operating principle of all optical gyroscopes. Based on the measurable technique of the Sagnac effect, it is possible to classify the optical gyroscopes. The two main different typologies of optical gyroscopes consist in active and passive architectures. In the active configurations, the closed-loop optical path, such as the ring cavity, contains the optical source forming a ring laser. The active configurations can be built in bulk optics or in integrating optics technology, although only the bulk optics solutions have achieved commercial maturity. Among the ring laser gyros, there are different categories depending on the method employed to overcome the lock-in effect. This is a condition for which the active gyroscope response results insensitive to low rotation rates, which occurs at low rotational rates, tens of degrees per hour. Lock-in can be reduced by introducing a mechanical dither, a magnetico-optic biasing, or by using a multiple optic frequencies configuration. Differently, in passive architectures, the optical source is external to the closed optical loop, such as a fiber coil, as in the interferometric fiber optic gyroscope. Ring laser gyroscopes and interferometric fiber optic gyroscopes, whose feature different in terms of size, weight, power requirements, performance, and costs, are the more diffused optical gyroscope technology. Sagnac effect. The underlying operating principle of almost all optical gyroscopes is the Sagnac effect. It was discovered in 1913 by George Mark Sagnac as a result of the study of the dynamics of Earth rotation by Michelson Morley and observation of electromagnetic wave in the non-inertial reference systems. Sagnac principle, as derivation of the general relativity theory, states that two counter-propagating optical beams propagating in a ring structure change their relative phase if the ring is rotating. Thus, it is possible to relate the phase change to the angular speed of the ring. As example, by considering an open circular light path of few centimeters and the rotational speeds of 1 revolution per second, according to the Sagnac effect, the optical beam's path difference is of 0.0000025 millimeters, which is too small for angular velocity direction. In 1966, the scientist Schulz Dubois, who was working at the embodiment of a ring laser-based angular velocity sensor, proposed a ring laser gyroscope shaped as a hollow cylindrical mirror, in which light described a circular path. To make visible the rotation phenomena in the ring cavity, two optical beams at the same wavelength but counter-rotating were introduced. The two optical beams reciprocally interfered and produced a permanent wave, stationary with respect to an external inertial reference system. The stationary wave is composed by nodes and antinodes, whether the mirror is rotating or standing. A detector is mounted on the ring framework, solidly rotating with it, so that during rotation, by counting nodes and antinodes of the standing wave through the detector, it is possible to evaluate the angular velocity of the ring. Indeed, the number of nodes is 2 times the length of the ring divided by the light wavelength. Knowing the number of counting nodes in the time unit is through the detector, it is possible to calculate the angular velocity of the ring. The scale factor can be expressed as a constant directly proportional to the ring perimeter and inversely proportional to the ring area. In reality, mirrors used for ring laser gyroscopes are never perfect. The mirror imperfections cause light backscattering and energy loss that give rise to a sort of interaction between the propagating electromagnetic waves and their moving medium. As a result, the permanent wave is no more perfect stationary with respect to inertial reference, but drifts following the rotation of the ring. Generally speaking, there is no relative motion between mirrors and standing wave, so that a false zero-speed signal is detected. This effect is called lock-in. Ring laser gyroscopes. The ring laser gyroscopes RLGs are based on a ring laser that is an angular cavity, where due to the Sagnac effect, two independent counter-propagating resonant modes intrinsically generated within the cavity through a gain medium show of a frequency shift if the cavity undergoes a rotation. The ring laser can be realized in a bulk solid-state optics or in integrated optics, although the integrated optics solution, semiconductor ring laser gyroscopes, are not commercially major. In one of the most diffused architectures, the RLG body is made from a triangular glass block. 3 air channels are drilled in the glass body and 3 mirrors are placed in each corner to create a triangular optic resonator. A low-pressure helium-neon gas mix fills the 3 tubes. A high-voltage electrical discharge is applied through the 2 anodes and the cathode for electrically pumping the optical cavity. Due to the action of the electrical pump to independent counter-propagating laser beams, clockwise and counterclockwise CCV and CCW and CW respectively, resonating at the same frequency, are generated inside the optical cavity. By making a partially reflected mirror, it is possible to detect the angular velocity of the rotating system by reading the frequency change of the resonant behavior of the device or the interference pattern generated by the interaction of the CW and CCW, which are clockwise and counterclockwise laser beams, leading to a standing wave. The two readout techniques are covered by the physics of the Sagnac effect. At very low rotation rates, the mirrors, being imperfect, produce backscattered light, which couples energy from a CW to a CCW. The backscattered light acts as the mechanism of the frequency synchronization, a lock-in of the two resonant beams at low rates of rotation. Lock-in effect. The lock-in effect occurs only for the conditions of weak mutual coupling between the two counter-propagating laser beams. Usually the coupling is caused by different backscattering sources, depending on the adopted technology and architecture, and it results in a response in sensitiveness to low rotation rates. The operating region is called deadband. This backscattering-induced coupling between counter-propagating beams is also responsible for the creation of standing waves inside the resonant ring structure. These standing waves could generate an optically induced alternation of high and low index absorption regions, an optically induced grating, which creates localized refractive index variations or losses, increasing the coupling and the lock-in. Possible solutions for the circumventing this problem are represented by the dual-mode ring laser gyroscopes, in which a mechanical mechanism of oscillation, in which two modes oscillate simultaneously and interact to reduce the deadband, or by insertion of a mechanical mechanism of oscillation around the sensor axis. This mechanism of oscillation, called dithering, is usually based on a complex mechanical system, unable to completely eliminate the effect of the backscattering-induced coupling. Moreover, Sometimes the dithering vibrations cannot be applied to those ring laser gyroscopes mounted on platforms that are very sensitive to the vibrations. The other problems associated to ring laser gyroscopes, which is the mode completion, is due to the different gain-assisted photon enhancement between the two counter-propagating resonant modes, whose eigenfrequencies are overlapped. By making different the two resonate frequencies of the two counter-propagating modes, it is possible to avoid the mode competition. Integrated optics of ring laser gyroscope solutions are yet not mature for commercial applications. Critical parameters for RLGs. Its critical parameters for ring laser gyroscopes are, firstly, size. Larger ring laser gyroscope can measure lower rotation rates. The sensitivity of large ring laser gyroscopes increases quadratically within the size of the optical cavity. Secondly, mirrors. The mirrors are fundamental elements for focusing and directing the laser beam to form the optical cavity. Thirdly, stability. The gyroscope body must be built within a substance that changes minimally in response to the temperature fluctuations. And finally, gas. Helium-neon generates beams with the most desirable features for large ring lasers. For gyros, in principle, any material that can be used to generate monochromatic light beams is applicable. The RLGs cover the high-performance market. Size and weight of RLGs and other limiting factors, mainly due to the body and the mechanical dither assembly. Miniaturization of the RLGs leads to a decrement in their reliability, reason for which integrated optic miniaturized solutions did not achieve a commercial diffusion. The power requirements of RLGs are high because power sources of several hundred volts at low currents are required.